Hey, Lee Robinson here from American Sentinel Canine. So we're going to drop this video in a few places as we discuss the value of gameness in hog catch dogs and also in protection dogs. So this topic is something that I see misunderstood by a lot of people, but we're going to do the best that we can to share it with a few people and see if this works. Okay, let's see. Give me just a minute. I'm going to jump on my phone here, and if you'll share the link to your pages or to the groups that you're interested in, some of the other people that are around may actually value this topic. It is a topic that is misunderstood by a lot of people, and as a result of that, I would like to see people get a better understanding of it. Some people think gameness is an all or nothing type of thing. Some people think it comes in degrees. Some people think it's a recessive trait. Some people think it's a monogenic trait or a polygenic trait. And some people think it doesn't matter in a protection dog. But we're going to look at this from a genetic standpoint. Yes, I've got a lot of experience with this, with genetics and working dogs for a long time. And I'd like to shed some light on the topic from a genetic standpoint that will help hopefully bring other people to enlighten some other people to how this actually works and why it's valuable. Because a person that understands genetics will be able to follow what we're talking about. And even if you don't have a good understanding of genetics, we're going to make it clear enough where the layman can comprehend, so to speak. All right, so let me share this link here, and let me share it with a few more places. I'll drop it in a few groups. We have to be a little bit selective. Well, no, we'll be good. It'll be all right. I was going to say a little bit selective. Some people aren't going to want to hear about this in guard dogs or protection dogs, but that's okay. They don't have to agree. We're going to talk about, at least they'll get some knowledge on how gameness actually works from a genetic standpoint, and whether it's an all or none type of thing, and how we know this. Oops, I'm almost done sharing it. If y'all share it too, I would certainly appreciate it. Like I said, like and subscribe to the channel if you like these type of topics. We'll try to bring more of them to you. I'm almost done. Let's see, that was the Jeep group. And one more time. All right, let's see. Nope, we don't want that one. All right, that's it. All right, so enough with that. So, gameness, what is it? Basically, the short summary description of gameness is the will to continue a task, the willingness to continue a task despite stress. Without, and by without stress, what we're talking about is without concerns for self-preservation. Being exhausted doesn't stop the animal. Being injured doesn't stop the animal. Pain tolerance or enduring pain is not a concern. There's a lack of self-preservation. This is what basically gameness is. And I'm going to do a share screen to do a simple monogenic trait here. Let's minimize this. Let me open a new tab, and we're going to share my own personal screen. And let me create a table here for y'all to see. Insert table. All right. So, because people don't really get a great understanding of this stuff, let me go ahead and share screen, present, share screen. And we're going to go to Windows. And this tab here, this is just a blank document. All right, so we're going to look at what's called simple dominance versus recessive. A lot of people think that gameness is a recessive trait, and look, it's really just not. And I'm going to show you how I know it's not a recessive trait. All right, so a dominant trait is expressed in both a homozygous and heterozygous condition. What that means is if you have, let's say big T is equals a dominant trait, and let's say little t equals a recessive trait. All right, what this means is if you have big T, you're going to get dominant trait. You're going to see the dominant trait. If you have big T, you're going to still see the dominant trait. So dominant is going to mask, or, whoa, let's see what's going on there. Can y'all hear me okay? Let's see what's going on here. Can y'all hear me? Oh, okay, good. Yeah. So a dominant trait, think of my hand as like a big T and my face is like a little t. If I have my hand in front of my face, the dominant is going to mask what's behind. So if my face is the little t, you can't see my face when the dominant is present. Now, what if we have two hands and no face? You're still only going to see a hand. So if you have two hands, two big T's, or one big T, in either case, you're not going to see the recessive trait underneath. What this means is you're only going to see the recessive trait when it's by itself. Okay, so let me go back to that window. Where is it? No, that's not it. It's a blank document. Did it disappear on me? All right, here it is. All right, so little t is going to be the, whoops, it won't let me do that. All right, little t is a recessive trait. So the reason why we know gameness is not a recessive trait is because if we had one parent that was, let's say, little t, and what I mean by that is, remember, we have an X chromosome and a Y chromosome. Let's say this is the female, right? So if this is the female, we have the female's father. Oh, goodness gracious. The female's sire gave her one gene, and let's say he gives a little t. And the female's mother, oh my goodness. There we go. Female's mother, and let's say she gave this female a little t. That means this female would be little t. She'd have two little copies of the t. Now, if the little t was a recessive trait, then this female would be homozygous recessive, and she would be game if gameness was recessive. Now, let's say we're going to breed that female to a male, and this male's sire gave him a little t, and then the male's mother gave him also a little t, then he would also be what's called homozygous little t. Now, this means the male would be game and the female would be game if gameness was a recessive trait. Well, if that was the case, no matter which combination we got, the female sire with the male sire, we'd have a game dog. The female sire with the male's mother, we'd also have a game dog. They both gave a little t. Here we'd have the same thing again. And then here we would have the same thing again. Every combination would be big T, little t. Well, gameness doesn't work this way. My point here is recessive traits are very easy to breed what's called true. They're true breeding traits because when you breed a recessive with a recessive, you're going to get nothing but recessive. And this is why, believe it or not, a dominant trait is actually harder to capture than is a recessive trait. And a lot of people don't understand that in genetics. So let's look at a comparison here to show you how a dominant trait is actually harder to capture than is a recessive trait. Now, with that said, I'm not saying that gameness is dominant, because it's not. But let's just say you have a dominant, or a dominant, this is going to be a heterozygous, dominant recessive with another heterozygous dominant recessive. Now, in this case, we would have big T, and here we would have big T, little t, and here we would have big T, little t. So now, when we breed two dominant individuals, because they are heterozygous, we actually get both types. We get the dominant type right here, and then we get the recessive type right here. Okay, and then we have two others that are heterozygous. That means they have one of each gene, big, little, big, little. All right, gameness does not work this way either. Now, with that said, it also doesn't work like this. All of these examples are what's known as a monogenic trait, meaning we're only dealing with one gene. It's just going to be the T. All right. So the male would be big T. The female would be big T, and this the squares here inside, as a result, would all be big T for whatever this trait is. All right. And so in this case here, again, gameness does not work this way. Now, you might think, well, Lee, how does this make dominant more difficult to reproduce than recessive? Well, recessive is very easy to reproduce because when you have two recessive individuals, every offspring is going to display the recessive trait. All right, let's try another example. What if one parent was homozygous dominant? Oop. And the other parent was homozygous recessive. Now, every single individual would be heterozygous. Okay? And here, if gameness was dominant, here we would have an all game litter, but these offspring, because they're all heterozygous, they wouldn't be able to reproduce that. Okay? That's if it was dominant, which again, it's not. And I'm going to be able to show you why it's not. Regardless of which one of these examples we have, because these are all monogenic, meaning they're only involving one allele, just the T's, then no matter which combination we have, they would all be fairly simple to reproduce. Okay, because this is all monogenic. Now here we have big T here, and then little t here, because this would be a heterozygous bred to a homozygous recessive. Again, gameness does not work like this. So when I talk about gameness, imagine that we have, let's say here's a DNA strand. Okay, this is not the way it's going to really be, but I'm just drawing. It's a strand with two sides. All right, we're going to get one set of, well, that's not really that good of an example. So let me go to my StreamYard and try to just do it visually, minimize this and maximize myself, or at least make myself bigger. So we have a set of chromosomes where you're going to have a set of DNA that comes from the mother and another set of DNA that comes from the father. And a lot of times we refer to these chromosomes as like X's, or in the sex chromosome, you have an X and a Y. But in reality, when we're making the sperm and the egg, what happens is those chromosomes split in half. And so it's no longer going to be an X. We call it an X, but it's only going to be half of an X. It's more like a parenthesis. You just have one side of it. The two parentheses make the X, but one side is just going to be, so it's kind of like a chromosome might look like that. Okay, so let's make this a lot bigger. Okay, and it may even have a little dot in the middle where it's going to be connected. Well, what happens during meiosis is these chromosomes become separate. And you don't just do this for one of the chromosomes. You do this for humans, it'd be 23 chromosomes separate. And in dogs, it's going to be 39 chromosomes separate. And when they separate, each one is going to become in its own cell. Right? So you're going to have 23 for humans in one cell and 23 in humans for the other cell. And all those chromosomes would separate. Well, for dogs, again, it's 39. So if we go to my website, we can see, let me go to my website here, and we'll see what a canine karyotype looks like. We're going to share a different screen. Present, share screen. All right, and I'm going to go over here and log in to Canine Genetics. I've got to sign in. And this is what a dog karyotype looks like. Now, if we look at these really closely, it looks like this is just a line, but this is actually two lines. Like, imagine two earthworms really hugging each other tight, and then you got another two right here. So what happens and maybe some of these we'll see them separate. Like here you can see on number 35, you can see that this is actually two sides. It looks like a little X, kind of looks like an 8, but it's really supposed to look like an X. On here you can kind of see it's an X. let's see here, you can kind of see the space in between them. So you got one here and another one here, one here and another one here. And so what's going to happen in meiosis is the first, this one of these comes from this 28, one of these comes from the mother, and one of these comes from the father. So in this case, we have an X and a Y. So this is a male. So this one comes from his father, and this one, or excuse me, this one comes from his mother, and this one comes from his father. But when he goes through a cell division called meiosis, these two are going to separate. One's going to go to one side, and then the other one's going to go to the other side. And that's in meiosis 1. Now that happens a second time in something called meiosis 2. And in meiosis 2, this side here will actually separate from that side there. So you'll end up with 4 cells. The first 2 being divisions of these, and the second 2 being divisions of these. Okay. I'm hoping this is showing okay. Okay, so I'm trying to find one that's got a little bit more of a line between the two where you can kind of see them. On number 7, we can kind of see that there on number 7 if we zoom in. So on the first division of meiosis, we're going to separate this one from this one. And then the second division of meiosis, we'll separate this from that and also this from that. So now you'll end up with 4 separate strands for this one chromosome, chromosome number 6. Okay, and we do that for all of them. And then that's going to, each one of these is going to be in one of 4 cells for this individual. Now, when that happens, and fertilization occurs soon thereafter, we're going to recombine these chromosomes from this male to the chromosomes that the same thing happened in the female when the egg was made. And when you recombine those, you have genetic recombination, not only from fertilization, but also from meiosis. Okay, so meiosis is going to cause these chromosomes, when they when they pull apart, sometimes they'll trade parts. Like let's imagine a deck of cards. If we take a deck of cards and, oh man, could y'all see that screen? I didn't have it zoomed in. Do I need to go back and do that part over? I see I didn't have it zoomed in. Let's do that again here on that chromosome, because I'm not sure if you could see it. So, all right, so we're going to go back up here to number 6. So for each one of these, in a stage called meiosis, these chromosomes are going to get pulled apart. So for here, we're looking at chromosome number 6. One of these is going to go to one side, and one of these goes to the other side, and that's going to become in 2 separate cells. And then those 2 cells are going to divide again. Each one of these is going to then, in the second one, this side is going to split from that side. And then in the other cell, this other one over here, this side is going to split from that side. So you have a total of 4 cells created from 2 cell divisions. We can get another image of this if we look at meiosis 1 and 2. Pictures, share this tab again. Oh, let's look at here. All right, so, and we'll get back to the gameness in just a minute. So this is all prophase 2. That's metaphase. Oops, man, I'm sorry, my screen's kind of bouncing. Let's exit that. This is a better image. Here we go. This is the image that I want right here. All right, so in this image here we have 2 chromosomes. You might think that's 4, and it is 4, but it's 2 from each parent. Okay, so we have, if I could, yes, that's going to be 2 from each parent. So what happens is you have, yeah, that's right. We got 2 from each parent. And so what happens is they copied each other to create the X's, and then the X's get split apart, and you have 2 chromosomes in this one and 2 chromosomes in that one, and they go there. And then these chromatids get pulled apart, and you get 2 chromatids here. So at the end, you have 2 chromatids, because the diploid set in this individual is just 2. Okay. Now it'd be nice if they would show you one with more than 2. Let's see if we can find one with more than 2. Maybe this one. They normally keep it simple, because when you get too many in there, it gets kind of crowded. But at the end of the day, imagine this happens with all 39 chromosomes, right? So if it happened with all 39 chromosomes, you would end up with a massive combination of genes that are very much scrambled. So it's like cutting a deck. If we had a deck of cards and you had, let's just say, basically 4 chromosomes. You have the hearts, the diamonds, the spades, and the what is it? Hearts, diamonds, spades, and clubs. I don't play cards, but that would be it. But then each one of those you have ace through king. Well, let's say those are positions on the chromosomes. So you have the position number 1, position number 2, all the way up to what is that going to be? 14 at one ace. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10. And then you have the jack, king, queen, and king. So 13 cards. So you'd have 13 positions on each chromosome. Well, when they cross over, it's like shuffling the deck. So we're mixing it up, and that's going to be one form of recombination when those chromosomes are pulled apart. So you have genetics recombination when they're pulled apart, and then you also again have recombination when fertilization puts that new set with that's found in the sperm with the new set found in the egg, and we're recombining those genes in a different way. So recombination kind of happens in 2 places. One in meiosis, and then again in fertilization, that recombines these traits in a new way. And that's why this simple let's see if we go back to here. Now I need to remove this screen and share a different screen now. So now we're going to go back to looking at these. I need to go to Windows. Share. Okay, so going back to here. So imagine we have on this chromosome a bunch of locations. Maybe in this one chromosome there may be, let's say there's 22,000 basically in 39 chromosomes. So we're going to what's called loci, and so we're just going to round about it, basically like 400 loci in one chromosome, 500 loci on one chromosome. The chromosomes are different sizes. Some of them may have 1,000 loci, some of them may have 500, some of them may have 200, and some of them may have just a couple of dozen. And a loci is like an address. It's a region on the chromosome. And then these loci are all going to have different genes. So now don't think of it just being big T, little t now. We're also going to have other traits. So you might also have, let's say, big P or little p. Okay, you might have big A or little a. You might have another trait that maybe doesn't have just 2 alleles. Maybe there's 3 alleles. Maybe you have big A and A prime, and then also little a. Okay, blood type, for example, you have I, A, and then you have IB, and then you have O. You have 3 blood types for humans. We have 3 blood types, and these 2 are dominant, or actually these 2 are like co-dominant, and then this is a hard recessive. So you have 2 that are equal in strength, and one that's recessive. Now, when you have this is what's known as a multiple allele trait. So when a loci has multiple alleles, or a trait has multiple alleles, that ends up with a multitude of blood types, because you could get homozygous A, or you could get homozygous B, or you could get heterozygous AB, or you could get homozygous little I, which is going to be O. Okay, and that's going to be your little I for O. Okay, little I is going to be the type O. Okay, and so you have here 4 phenotypes that are controlled by just 3 genotypes, depending on what you got. So if you got IA, you get type A blood. If you have IB, you have type B blood. If you have IA-IB, now you have type B blood. Oh, excuse me, AB blood. Oh, my bad. Something must have happened there. I need to be careful how I type here. So now we're going to have IA-IB, IB, and that's going to be AB blood. And then you have little I, which is type O. So that would be how blood type works right there. Okay. There's my dash there. Okay. Sorry for the typos. Okay. So that's how that would work. Well, what if you have a number of factors that affect you? Now, in gameness is going to be more like body weight. And so what I mean by that is body weight is not going to be controlled by just a single location in the genetics. It's going to be controlled by a multitude of things. So you're going to have genetics that have your bone density. That's going to affect your body weight. Then you're going to have genetics that affects your muscle mass. That's going to affect your body weight. Then you're going to have genetics that affects your growth hormone level, which is going to affect your body weight. Then you're going to have genetics that influence what things you like to eat. Well, that's going to affect your body weight. And so you have a multitude of alleles that are coming in where now it's not just A or B. And it's not even just AB or O. There's a multitude of things, literally like dozens of things that can come into play to affect your body weight. And this is how gameness works. And the reason that we know gameness is going to be a polygenic trait is instead of a monogenic trait is because when I was just doing these simple traits here, in this picture, and we were looking at these, none of these problems are really that complicated. All of these problems could be purified in just a few generations, and the population would breed true. So if we wanted to isolate this trait and separate it so all of the individuals in that population displayed the same phenotype, that would be very easy to do in just a matter of a few generations. But what do we know about game dogs? It doesn't work that way. Okay, it's producing game dogs consistently is a difficult thing, and that's because it's not a simple monogenic trait. Like body weight, it's influenced by many factors. So you can breed like an average sized person with an average sized person, and you get some that are bigger and some that are smaller. You have that bell-shaped population distribution, that bell-shaped curve. And so some of them are going to be more extreme, and some of them are going to be less extreme, or more in the norm. Or there's two extremes. There's the high extreme and the low extreme, and then there's the norm, right? And so the bell-shaped curve has the majority being in the middle, all right? And then out at the end, it's hard to do this because everything's backwards on the camera. So I have to find the center of the screen. So on that bell-shaped curve, the extremes are at each end. You have the hard curve that won't defend itself at all, and then you have the extremely game dog that's going to defend itself no matter what, or not just defend itself, pursue combat no matter what, pursue its will, whatever its desire is. Whatever it wants to do. If it's a sled dog that runs 2,000 miles to its death, that's not the same as a game dog in terms of like the American Pit Bull Terrier, but it's still a degree of gameness to finish its task despite its own well-being. Okay, so that dog that runs 2,000 miles, you might think, Lee, what are you talking about? That's a sled, 2,000 miles, okay? That's a long way in the Iditarod race, 1,000 miles, long way in the Iditarod, in extremely cold conditions. That you have to be a pretty hardy animal to do that. Now, obviously, your average husky is not going to qualify for that type of venue. That takes an extreme individual that has been selected through generations and generations and generations to be determined to finish a task no matter the stress. Despite the stress, it's going to continue. And this is kind of what gameness is. It means the desire to continue. It's like a rheostat. And because there's so many traits that come into play here, it's hard to reproduce, but that's also why it's not a yes or no. Because body weight is not a yes or a no. It's not like you have brown eyes or you have blue eyes. It's not that flip of a switch one way or the other. It's a rheostat, a dial, where it flows, becoming more willing or less willing. And the game dogs are going to be the ones that are so willing that it becomes difficult to find their breaking point. These are ones that are going to be willing to work to exhaustion, work through injury, work through shock, work through pain, work through being dominated. The desire to continue even when they're dominated, in shock, in pain, out of oxygen, on the bottom, and nothing's going their way, but yet they still think they're going to win. All right, that's what gameness is about. Now, why does this matter in a hog dog, and why does this matter in a protection dog? Well, if somebody was to, let's say, break into my house, especially if I'm not home, and maybe that's all that's here is my daughter or my wife or something like that. I don't necessarily need the dog that's the biggest and the strongest to subdue that person if they're, especially if they're not committed. If they're not committed, they could get scared and run away, right? So what's more important than the size of the dog that's in the fight is the size of the fight that's in the dog. Because even if it's a smaller dog, the more game that individual is, the more likely it's willing to stay in combat, should it be willing to engage to begin with. Now, sometimes you can have a dog that's not willing to engage and it still could be game in some other venue. But for hog hunting or protection work, you need it to be willing to commit or engage during the selected task that you're looking for. So when we're looking for gameness in like the American Sentinel, we're using the American Pit Bull Terrier's gameness from its ancestry from combat and trying to redirect that to be used for either hog catch work or protection work. Now, here it's important that the breeder is honest about what they have, because sometimes a dog can be excellent in one venue and not so good in the other, but still be a great dog as a total. So we have some dogs that when they are more prone for animal aggression, we will use them for the hog hunting. And then we have some that are capable of doing man work and we'll use them for protection work. And not all types of protection is the same. There's personal protection. There's sentry work. For sentry work, you're going to need a little bit more defense than you would necessarily need for protection work, because protection work, the person is there and now you're able to give commands. And this is going to have more overlap to like sport venues. So a sentry dog is going to need to be able to work without a command and is going to need a little bit more defense. A protection dog, however, can have more prey or more fight if the owner is able to give a command. Now, sometimes you'd still need a little bit of defense, because what if you can't give a command because you got knocked out, okay, and hit from behind or something like that? So then there's still, it's not a simple one-trick pony where one dog is going to do everything. Some dogs that are really good in one venue may be terrible in another venue. If you have a dog that's really defensive, and it doesn't have any prey drive or any gameness or any fight drive instinct, those dogs might do okay in a small environment where there is no escape. Let's say behind a fence or in a car. There's a lot of people want to do huff and puff and bluff and think that it's enough. And it is enough when you have a fence or a small area and there's no option for flight, because gameness is not going to be measured when the option for avoidance exists. Gameness is only, or it doesn't exist, excuse me. Gameness is not going to be measured when the option for avoidance does not exist. You can only measure determination in an animal when the option to flight exists, because there's three responses to stress: fight, flight, or freeze. When it comes to adrenaline, and we know that adrenaline and cortisol, epinephrine, these things are associated with stress. So gameness is not measured unless stress is involved. And I believe that epinephrine plays a role in the expression of gameness. I think it's a cortisol response, because we know that cortisol levels go up during a fight, flight, or freeze response. Fight, flight, or freeze is going to be something happens that, let's say you get attacked and there's three responses. You fight back, you run away, which is flight, and there's also freeze. That's that learned helplessness state where you like play possum. Well, and then there's also a unique thing in game dogs that's called cold. A cold dog is different than a cur. So with for the pit bull, you have the game dog who engages or fights back. You have the cur dog that runs away. And then you have the cold dog, which doesn't turn on. It doesn't fight back, but it's also not freezing. It's almost as if they have such a high pain tolerance and such a comfort in stress that they don't realize they're in a fight or flight or freeze response. And believe it or not, some cold dogs do seem to carry a lot of the traits associated with gameness. There's some sort of ability to deal with stress almost as if it's neutral. Maybe their pain tolerance is extremely high or something like that. Okay. What question? So somebody asked a question: what are the physical attributes of a band dog? Does it have bite, strength, etc., of the Mastiff blood? Well, obviously, we would expect the good band dog to have the strength and bite of a Mastiff, but also tenacity and athleticism, heat tolerance, agility, endurance, and stamina and malleability. and prey drive of the pit bull. That's a good one. You want both some defense, and the goal is to try to capture all the traits that we desire and eliminate all the traits that we don't desire. But that's going to take years and years and decades of selective breeding, because when you mix A with B and they're at opposite ends of the extreme, when you mix power with endurance, sometimes you get a powerful animal that has endurance. Sometimes you get a weak animal from the endurance sometimes you get no power, no endurance. Okay, is what I'm getting at. So like the powerful animal doesn't have any endurance. The endurance animal doesn't have any power. So when you're trying to capture the endurance from this one, you might get the non-power instead. And from when you're trying to grab the power from this one, you get the non-endurance instead. So when you cross those together, let's go back to our picture here. So this is an example. Let's say over here we're going to have little p. That means no power. Over here you're going to have big P. Let's say that's power. And on the next chromosome, let's say we have little e. And then over here we're going to have big E. So this one here with a lot of power, this one here has little power, this one here has a little endurance, and this one has a lot of endurance. Well, when you breed these traits together, if we were to do a polygenic trait, remember these lines do not represent just these alleles. These lines actually represent the egg possible combinations. So now from one we have big P and little e bred with little p and big E. All right. Well, if we delete that cell, let's just delete that. And then here we delete this entire row. And now we end up with big P, little p, big E, little e. Well, that's the first generation. And this is why an F1 cross of band dogs a lot of times work. So let's say the sire is got a little bit of power, but a lot of endurance. Let's say that's your pit bull. Let's say here's your female is your mastiff. You got a lot of power, but a little bit of endurance. Now you get your F1 band dog, your first generation band dog. You have the power and you have some endurance, but it's heterozygous. What's going to happen in the second generation? Well, in the second generation, you have a number of combinations you could get. You could get big P with big E. You could get big P with little e. You could get little p with big E, or you could get little p with little e. And because of that, when you're going to breed that together, you now have what's called a dihybrid cross, which is a big possibility. Instead of me drawing that out, let's just go back to StreamYard, and we're going to stop sharing this screen, and we're going to go to a dihybrid cross second generation. And so we're going to look up a dihybrid cross second generation. All right, and so here we're going to see you have, like, let's say that's the big P, big E, big P, little e, little p, big E, little p, little e. Okay. What happens here in the second generation is you don't just get power and endurance every individual. Here you got power and endurance. Here you have power and endurance, but an inability to reproduce itself. Here you have power and endurance, but again, an inability to reproduce itself. Here you have power and endurance, but now you have an inability to reproduce itself twice. Here you have power and endurance, but an inability to reproduce itself. Here you have power, but you don't have any endurance. So definitely not going to be, this is a hard call right here, right? Here you have power and endurance, but an inability to reproduce itself because of these heterozygous. Here you have power, but an inability to reproduce itself on the power, and then you have no endurance at all. So again, this is a hard call. Here you have, except same thing, inability to reproduce itself on the power, but you do have a good ability to reproduce on your endurance. Okay, here you have a little bit of both. Here you have the endurance, but no power. Here you have no power. You have endurance, but not a bit, but it can't reproduce it consistently. Here you have both power and endurance, but you again your inability to reproduce itself consistently. Here you have power, but an inability to reproduce itself, and then you have no endurance. Here you have no power. Here you have some endurance, but an inability to reproduce itself, and here you have no power and no endurance. So this is a hard call for both traits. So the only one in this table that's worth a darn is going to be this one right here: power and endurance and the ability to consistently reproduce itself. This is going to be your prepotent individual. Okay. All right. So, and that's what polygenics works like. But now imagine we're going to compound it, because that was just two traits affecting it. So that was polygenic because it was two traits affecting it. But with something like gameness, it's not just going to be two traits. It's going to be a multitude of traits, because it's even more complicated than that. Trust me, if it was just two traits, after 200 years of selective breeding the game dog, the game bred American Pit Bull Terrier, they would have purified it by now and consistently been able to reproduce if it was just two traits. There's going to be way more than just two traits affecting gameness, okay? Or way more than two alleles. So this is why I believe gameness is going to be heat tolerance, oxygen, pain tolerance, conditioning, schooling, which is environmental. That's not even going to be genetic. A lot of gameness is going to be a genetic trait. Most of it's going to be a genetic trait, because you're not going to be able to make a genetic cur a game dog, no matter how good of a trainer you are. You can get that dog to reach its potential in protection work or hog catch, but it's never going to be a committed individual that's able to reach its apex form. It's only going to reach its limit of its genetic potential. So then you have another dog that's got more of the desired genes, and you're going to slowly work your way up to having more and more capabilities. Okay, next. I see gameness in my pup. Danger Trinity. It's like a switch and flip people think. Yep. Trinity seems to be reproducing herself very well, and Danger seems to be a really good producer as well. Ryan Keaton has got a great dog in Danger. Okay. This is how you breed power and endurance. Well, it's kind of like that. Okay. There's going to be. I'm oversimplifying here for the purpose of a video. So obviously, if you go to the gym and you work on power, you're going to lose some endurance. And if you work on endurance, you're going to lose some power. And the reason why is one is an aerobic activity, and one that deals with increasing your testosterone, and one is a stress-related activity that deals with cortisol. And so when you're dealing with cortisol and steroids versus different types of steroids, cortisol is a steroid, but it's a steroid that kind of breaks down your muscle mass, and it has different side effects, and it's not going to be muscle growth. So you can build power by going and exercising and lifting weights and stuff like that. And but if you have to run a long distance, you're going to increase your stress, and then you're going to lose muscle mass to improve your efficiency. And so that's your environmental aspect. Your genetic aspect, though, is going to be basically what are you predisposed to? Are you endomorph, mesomorph, ectomorph, etc., that kind of stuff? Do you have a lot of fast twitch muscle or slow twitch muscle? Those type of things. I personally tend to be more of a slow twitch type person genetically. I remember in high school I could run all day. I would never get tired. I could run all day, and somebody else could sprint and blow right past me. Like I could. What was weird is when if I ran a mile, at the end of the mile, I could almost run faster in a sprint than I could if I was to do a cold, hard sprint. It was kind of weird. I think that what happened for me is, I think a little bit of the cortisol may have actually enhanced my ability to deliver my power, but I was never a really strong, powerful individual. I was always kind of wired for that endurance race. Somebody else is going to be maybe wired for the power race or power type of sprint type sort of situation. So like Arnold Schwarzenegger, you've heard me talk about him being predisposed to having a physique, and then he goes to the gym and he amplifies that, takes it to its full capability. All right. Well, that's a little bit about how genetics works. If you missed that at the beginning, genetics is going to be definitely a rheostat. It's not going to be on-off. It's going to come in degrees, and the reasons why it's going to come on degrees is because its mode of inheritance is clearly not a simple monogenic trait. It's a polygenic trait, And polygenic traits are always going to be expressed in degrees, like body weight is expressed in degrees. A simple trait that's on or off is going to be like freckles. Either you have them or you don't. All right, that's the way gameness works. Gameness does not work that way. You either have it or you don't. It doesn't work that way. If it did work that way, it'd be a monogenic trait like freckles. But it doesn't work that way. It's harder to reproduce than that. And therefore it's clearly polygenic because its mode of inheritance is complicated, influenced by many, many factors, and therefore it has to be a polygenic trait. And why does it matter in a hog dog or a protection dog? Because if you don't have commitment, you don't have the ability to stay in that battle. And so for a band dog program, it's important. And this is why the game-bred American Pit Bull Terrier is one of the key components in the band dog. I hope y'all enjoyed the video. If you do like it, please like and share. This video is applicable to the person that's interested in the game-bred American Pit Bull Terrier and trying to understand why it's difficult to reproduce. This video is applicable to the hog hunter or protection work person. This video is applicable to the band dog breeder. All right, is tested, not bred. It's both. It's tested and bred. Polygenic traits can be bred for, but it's like, let's say you wanted to breed the tallest people in the world. Could we breed people that are 9 feet tall? Yes, you could. But it's selected for by slow distributions over time. So you select for the traits. And by selecting for the traits, you're going to get more and more extreme individuals. So how would you make 9-foot people? Well, you'd have to go ahead and eliminate anybody that was under 6 foot. After you eliminate everybody that's from the breeding population, okay? So you don't allow those individuals to reproduce. Doesn't mean you have to euthanize them. You can put them in pet homes, right? But you're not going to allow them to reproduce. And so next thing you're going to look for men that are, 6'8" and women that are 6'2". You let them reproduce, and somebody's going to come out 7'6", and a man's going to be 7'6", and the woman's going to be 6'8". Then you make sure that you always raise the bar slowly. If you raise the bar too fast, you eliminate too much of the population that carry desired genes, and you don't know it because they're mixed in with other things that are suppressing their expression. So I might have some trait that would make me really tall, but it's blocked by another trait that prevents its expression. So by slowly moving the gene, the standard, slowly moving the standard up, you're going to actually slowly filter out the undesired without rapidly culling out the desired. And with slow selective breeding, you actually in time make more progress than if you do a hard cull, one slam, cull it out immediately. And so that's one of the things that we do as breeders that might actually be a mistake, is culling too hard. It's important to cull hard. Don't get me wrong. It's very important to cull hard. But the good thing about being a breeder, if you cull really hard on your yard and you restrict too many traits on your yard, you can still breed off your yard and bring something back in. So if you lost something on your yard, you can still probably go out and find it. But in the population as a whole, what if we culled the whole world really hard? Well, if we culled the whole world really hard, we would be eliminating a lot of the desired traits that are found in individuals that we don't even see. Because as much as we want to breed for traits, it doesn't really work that way in the real world. In the real world, we're actually breeding for to the individual that carries the good and the bad traits. We're trying to find just the good traits, but there's no such thing as a perfect individual. Every single individual is going to have some undesired genes, even if you don't see them. Even if they don't show them, they're going to carry some undesired traits. However, there's also going to be individuals that are undesirable that do carry some desired traits. And so we want to slowly raise that bar so we're filtering out the undesired traits while maintaining the desired traits. And obviously, since I can't keep 100 animals or 200 animals, I have to cull pretty hard, because believe me, if I produce 100 animals in a year, I'm not going to keep all 100 of those animals. I have to cull hard, otherwise my yard would be, I'd be bankrupt, and I would be, because I couldn't feed 100 animals. So we have to, and by culling, it means breed the best and separate the best from the rest. Okay, we got to separate the best from the rest. And so I'm culling hard to find those best and make sure those best dogs stay here or with other people that are going to breed, or at least pay for a high quality dog for whatever it is it's going to do, because the money that I get for those high quality dogs that I sell, that has to finance all the rest of the program. And so because we're not going to be selling the ones that are of low caliber for top dollar. We're just not going to do that, right? And even the low caliber dogs in one man's program, they may be phenomenal dogs compared to other programs, because the standards have been so high for so long that now the bell-shaped curve, or that average, has shifted up to a really high level of performance. So they may be better than someone else's stuff, but it's still, we're slowly trying to move it more and more to be stronger, faster, more heat tolerance, more speed, more agility, more endurance, more pain tolerance, more trainability, and more loyal, more prey, more defense, more fight, whatever, better recovery time. All these things are going to come into play. And so slowly over time, we capture the best and cull out the rest. All right. But it has to be done carefully and over time. I hope this video brought something to you. Let's see what the next question is. Anybody, do I plan on breeding cobalt? If no, it's off topic, but my wife wants a male. I do plan on breeding cobalt. Cobalt is a very tough animal. His only fault, he has two faults in my opinion. I'd just be open about it. Look, I'm an open book here. Some people will like to keep their secrets on what the faults are. Here's the faults with cobalt. He's a smaller dog for how he's bred. So he's 50% pit bull coming straight off of Frankie Bomp. That's a great plus. But Pele, being a Midgard Mastiff, she's almost 100% Mastiff. She's like 95% or something like that, really high percent Mastiff. So Cobalt's negative is he's going to be carrying a lot of Mastiff blood that goes back to Achilles. And whenever you're dealing with Achilles, that Neapolitan Mastiff, that's where any hip problems that we've ever had have come from, like Achilles. We've had very few, but every dog that I can think of that's ever had a hip problem was related to Achilles. Now, Cobalt's got good hips. I'm going to check his hips while we're on here because I don't want to say anything incorrect. But remember, a dog is not going to just reproduce what it is. It's also going to reproduce what it comes from. It says here that Cobalt, I might need to do Cobalt hips. I don't have his on record there on the website, so maybe I haven't done his hips yet. We'll need to take care of that if that's the case. So I'm going to take care of that this week. I'm going to call up the vet because we have an appointment tomorrow to drop off some dogs to get some ear crops. So I'll see if they can do a hip x-ray on Cobalt and get that taken care of. I need to know that about him because he's tough, man. He's got a really, really high pain tolerance. I already know that. And he's got good defense. He's got good prey. So let's check his hips and see what they are, because I want to make sure that we don't get any hip issues. And with him going back to Achilles, that would be a concern. But he's also kind of a small dog. So I like to save him for some of the larger females just because he is a small dog. But, man, he's tough as nails. There's no doubt about that. And if he has a hip problem, I wouldn't be surprised if I wouldn't know it, because he is so tough. His pain tolerance is through the roof. Very, very powerful animal. I seriously doubt he's going to have anything wrong with his hips. But again, like I said, I always have a little concern about too much Achilles blood, because that Neapolitan Mastiff, and it's not about Achilles. This is about the breed in general. Even if Achilles had good hips himself, he is a Neapolitan Mastiff. And if you look up the breeds that have the most hip problems, Neapolitan Mastiff is not my favorite choice for a band dog program. Yes, it's in our program, but that's because we look for the individuals that don't have those undesired traits, and Achilles didn't have it. But the population of Neapolitans in general does. That was one of the concerns that comes with the Neapolitan. I'm surprised that so many band dog programs really like the Neapolitan Mastiff. It's not my favorite. Okay, I like the English Mastiff more and the Tosa Inu more. But the Neapolitan Mastiff does bring some good attributes to the table if you select wisely and you're honest about it. All right, the reason why I asked is because I saw a working video and the guy talked about how strong the bite was on the suit, but the dog looked like he was tireless. Yeah, Cobalt's tough. There's no doubt he's tough. I don't know if you're talking about, it may have been a different person. Reggie Jackson. Who was he talking about? Let's see. Oh, he's talking about power and endurance. Yeah. Look, that's just a matter of what's going on there is the dogs are powerful because of how they're bred, and then they're conditioned for endurance. So it's kind of like taking Arnold Schwarzenegger and then conditioning him not for power, but conditioning him for endurance. And because he's conditioned for endurance, he's going to have endurance, but he already has an innate instinct for power because he's made that way. So that's kind of like the perfect band dog. The perfect band dog has power because of how they're built, their genetics on how they're built. And then the way we condition those dogs is going to be to make them tireless. Okay, that's how that works. From what I've seen online, I suspect rejects are better than a lot of people's best. I don't want to be braggart, but I think you're telling the truth. I think you're calling it like you see it. This is why I love this guy. He's always straight up tell the truth. He doesn't lie about his dogs. I'll be getting a female from you once my next place lines up. Thank you very much, man. We appreciate it. And hey, sometimes things don't work out, but if they don't work out, we're here to take care of you. I have my deposit ready. Let me know what female. It's Cobalt. All right. I don't know your name here. Do it all clean. LLC wallpaper installation. So send me a message so I know who you are. That way I can let you know when I decide what I'm going to breed Cobalt to. But I'm going to go get his hips done tomorrow, and what they are we'll be posting. So keep an eye out on his hip X-ray. We'll drop that. Well, let me say that. If the vet's able to do the hip X-ray tomorrow, I'll do it tomorrow. Usually they can. If they can't do it tomorrow, then we'll do it when they pick those pups up. They're getting their ears done tomorrow, so I'll be picking them up Wednesday, and maybe they can do an X-ray either tomorrow or Wednesday. All right. Grom is coming out of his shell and looking really good. He's growing fast and looking good. I'm glad to hear that. All right. Well, I'm going to go ahead and sign off with that. It's almost been an hour. Again, hey, like and share if you get something from this. I appreciate your support. I don't ever ask people to like and share if they don't get anything from it, but if you do get something from us, please like and share. We really appreciate your support. Y'all take care and have a blessed day.